Okay. Yeah. You can hear me, no?
Yes, sir. Beautiful.
How many participants are there?
Almost 50 to 60 participants are joining.
50 to 60.
Yeah.
Okay.
So here from our India, around 20 participants are there, and most of the participants are from Africa. From Nigeria, most of the students are there. From other countries like France, Malaysia, some one or two students are there from each, and from Sri Lanka, so one or two is there. So they all know the basics, okay, on the speech, and within these 3 to 4 days, they know a little about the speech processing.
Okay. What is the background of the students?
Maximum students are from BTech background, but most of the students also from MSc, MTech, and some PhD scholars also there. But they don't have much knowledge about the speech processing. So that's why I can start from the basic only. But many of the persons has resource person has already taken, like Murli and Dilip has already taken this fundamental of machine learning.
Yeah. I spoke to Murli today, so he gave me some background.
Yeah, they have already taken the thing, and today also Dr. Bina also taken some session on the keyword spotting and spoken form detection.
Okay.
So your, I think, sir, source separation is speech and music, na?
Yeah.
Sir, actually, yes, we'll start the session. Let the student join. So one of my PhD scholars, I also don't have much knowledge on the speech processing. So he is a musician actually. Okay, and he does not have much knowledge on the technical knowledge, very less, but he's a musician, so he wants to pursue his PhD on music. Okay, he knows classical music, Hindustani, and this modern song. Okay, he can ready the data set. So if you can do some collaboration, if you can help him and me also, how
Sure. Yeah. He's joining the talk today.
I think he will join.
Okay.
Okay. Randeep Palit, his name is. So we'll discuss that one also later.
We can discuss that. Yeah. Sure. I am open for any collaboration with for music and all that. Yes, I'm very interested.
Yes. Actually, he's a musician and good musician on classical music.
Okay. I mean, my knowledge about music is also limited. I just started maybe 2-3 years back. So.
Okay. So I am in zero, so definitely I'll need your help. Yeah. Okay, Deep Sankar, I think I've just introduced to Padmanabhan sir. Then you can start. Deep Sankar.
Sir, Ankisha will.
Yes, Ankisha, yes. Yeah.
Good afternoon, everyone. It's a privilege to introduce Mr. Padmanabhan Rajan, a distinguished scholar from the Indian Institute of Technology, Mandi, renowned for his expertise in machine learning and signal processing. With his significant contributions to speaker verification, audio processing, and bioacoustic classification, Dr. Rajan has propelled advancement in these domains. His research has not only enriched academic but also fostered practical applications in various fields. Please join me in extending a warm welcome to Mr. Padmanabhan Rajan. We eagerly anticipate insights on source separations in speech and music. Thank you, sir.
Yeah, thank you.
Welcome, sir, once again. And now session is yours.
Okay.
I just share this.
Yes, share my screen. I hope participants can hear me. Can we ask questions in between? I mean, is the session? I mean, when can they ask questions? They ask questions in the end, or can in between also they can ask?
Yes, that is your choice. No.
Okay.
If you give permission, they can ask in between, or at last also after the session they can ask.
Yeah, sure. Let me try to. Okay, let me try to share my screen. Okay, what is this? Select a window or applications.
So individually you have to select. I think open the PPT, then only which window you want to share, that you have to select. Either multiple window or single window that you have.
Okay.
I have to open the PPT, then only just.
Yeah, I opened the PPT. Let me. I have to share sound because I may be playing some sound.
Yes, yeah. A screen is coming, sir.
Which screen is coming?
Yes, yes, it's coming.
There are two screens. I have two screens. Which screen is being? What are you seeing on the screen?
Padmanabh has started screen sharing. This much only is there. I think it will take time. Nothing is, and blank screen is there. Some line has written only, has started screen sharing.
Let me see. Let me just once again. Let me try it once again. I'm also not seeing anything in the share, but it's not letting me choose what to share.
You just open the PPT first.
Yes, I have opened the PPT. I have opened PPT.
Then go to sharing. Then you have to choose that particular window.
Yeah, but that option is not coming for me. Let me. I'm using Linux, so I don't know if that has anything to do with it. Share sound. Usually it should ask, no, which screen to share and all that.
Yes, yes, that is coming in my case. That is coming.
Yes. Meeting में. Nothing is visible for you?
No, sir.
I don't know why it's not coming. Computer audio. Let me try again. No, it's not. I am also not able to see anything. It is not. Blank screen is coming.
Given the sharing option as I've already given, allowed that share option.
Yes, but can you see my mouse or something? Can you see?
No, sir. Nothing is there. Can I switch over to Windows, sir? Or if any problem is here, or window is not there?
Sorry, what?
Oh, window is there in your system or no? Linux?
No, I don't have Windows. No, I use only Linux. Summary. Why is this post share?
And option is not coming, now. In Linux, I do not.
I'm not getting the sharing of. I mean, it's showing to share, but the sharing is not happening. I don't know why.
So let me make you the co-host, okay? So now you are the co-host, okay? Now you can try, sir.
Okay. Advanced video.
Try one, which is possible.
Nothing is coming from me.
No, sir, nothing is coming. Only that Padman has started screen sharing. This much is showing.
And now I cannot see the sharing also. Where is the...
First, sir, otherwise open the PPT or PPT has opened already.
Sorry, what?
Must open the PPT first, then only from here you can choose that particular window.
Yeah, but I'm not getting the zoom now. Where is the PPT I have opened.
Okay, okay. It's showing also. Means you are sharing the screen, it's showing that message only.
How do I stop unsharing? No, I cannot unshare.
No option is that one share again.
No option. I'm not seeing the option to unshare.
End option is there, na?
No,
Or
I'm not
let me
seeing.
end from my side. Okay.
Yeah.
Screen sharing option. Okay. Now my
Okay.
screen is shared.
Yeah.
My screen is coming now. Then I am stop sharing. You just try. You just try it now again. Yes, Akashdeep.
So may I suggest something?
Yes, definitely.
Sir, if one sir can send you the file and you screen share, he
Yeah,
can
that is
he
there
can
in
use
my
the
mind.
mouse over. He can use the mouse over to use your computer.
Okay.
There's the option.
Okay, that will do. Otherwise, let search try once, then only you can do this option. I am also thinking for that one. Thank you.
Can you hear me?
Yes.
Uh,
You just reshare. Otherwise, sir, you just send me the PPT in WhatsApp also you can send so that I will share it and I will give the option of the mouse share option to you.
is there a Google Meet or some other option?
No, sir. So, that we can do, sir. Na? You just share me the PPT and I will share from my system and I can give you this mouse over permission so that from there you can.
Okay, wait, let me. Yeah, the only problem is that this PPT, it's not a PPT, it is a PDF file. I mean, it has media content and also I don't know how it will come properly. We can.
Why it's not sharing? I don't know. It's showing, but why it's not sharing?
I'm not able to. I'm not getting the screen back. The Zoom screen is not coming.
Okay.
I think it's some Linux issue.
Yes, I think.
Okay.
Again, if I'm going to share, then yours that will be stopped. Suppose I'm now sharing, now yours will be stopped.
Yeah. You keep it like that. I'm replying to your email and I'm attaching the presentation.
Akashdeep, from where will get the mouse over that permission?
Sir, after sharing, at the top the option will come.
Okay,
Like
fine.
the annotate and all that comes like that.
Okay, fine.
Okay, I've sent you the presentation.
Okay, sir. Let me check. In my mail, sir?
Yes, in the same email which you sent me.
Okay, fine. Yeah. Now what? So I will download all the files or one file is there?
One
file.
PDF file.
Okay, fine. So now I'll share that one.
Yeah, yeah. So how will you control now? I have to tell you to go to the next slide like that.
Yes, yes. I think you can control that one. Akashdeep, you just help him, help sir to how to give the control.
Yes.
Okay. So which one? The PPT is open. Na? Okay. So let me share the screen.
Yeah.
So yeah, got it. And share audio, nice video. And select window or application you want to share. Yeah. Share. Now it's visible.
Yeah, yeah, yeah.
Now yes. How to give the control, Akashdeep?
Sir, for once, if you go to Zoom,
Okay.
Can you hear?
you
Hello?
see
Yes, I'm with
Padman
you.
sir's.
Yeah, yeah, sure.
No, I'm. Satya sir, can you see Padman sir's video?
Yes, video.
Everyone.
Now I have
Uh,
already shared.
you
Okay,
to take
Padma sir video.
the
Okay,
mouse and
why
go
you
there.
telling I have to go to video of the Padmanabhan sir.
Yes, yes. And when you take your mouse there, the 3 dots is coming in the corner.
Okay, fine.
A 3 dot in a blue box.
Fine. So
There you
yes,
should
so 3 dots are there. So here,
click on that.
okay,
Or is there a mouse option there? It should be there.
no mouse option is there. Chat, stop video, pin, spotlight tip for everyone.
No.
Make post, make co-host. Sir is already co-host. Yes. Then
Let me just try it from a different computer. Okay, I will just see. Right.
So have you the sir Windows system is there with you?
No, I don't have Windows. I have another Linux system, but
Okay, you can try for there. So, but here no option is there for the mouse.
So when you're sharing that place, annotate and all that options is there.
hey, hello, can you
Yes.
it's no, because I will just talk. So if you can
Yes.
if you can just move the slides, that is enough. I don't need too much input.
Okay, sir.
So,
Definitely.
rather than wasting
So
time.
I think we can start.
So you are sharing the screen, right?
Yes.
Is it visible to the participants? Please check with the participants. Participants, are you able to see the screen?
Yes, sir.
Okay, fine.
Okay, sir, you can start. Sir.
Okay, we can start. So, one second, like my slides. Okay, can you please come to the first slide?
Yes, sir.
Title slide, yeah. Okay, I'm seeing one bar in my screen. I don't know. I hope maybe it is not there in your this thing.
Yeah.
Can you see the screen properly, or is there a black bar in between?
Yes, sir. The black bar.
Black bar, even I'm able to see.
Is
I
it
don't
okay
know.
there?
Okay, now it's fine. Now it's fine. I think no, it's coming and going. That black.
Yes. Yeah, that one actually the screen that status bar of myself.
No. There is something is covering the screen, but most of it is visible. Okay. Can you go to presentation mode? Is it possible to go to presentation mode?
Okay, there is the PDF. I don't know what the presentation mode.
Control L, I think, no?
Okay. Yeah.
Or F5. Yeah. Control L.
Yes, sir.
Okay. Yeah, let's start. Already we have lost some time. Okay. Good afternoon. So I'm Padmanabhan, and I'm a faculty member in IIT Mandi in Himachal. And today's talk is on source separation in speech and music. So this some of the research results which I show later in this slide in the talk is joint work with my master's student Rajesh, who recently graduated. And yeah, he was the one who started working on source separation in music. Okay. Yeah, next slide, please. No, there is one more slide in between. Yeah. But yeah, since he's not sharing it, yeah, so if let me see if I can, because it's not there here. Let me see if I can play out some sound. Wait. Can you? Okay, I don't know if you can hear the sound, but let me know if you can hear something.
No, sir.
No, sir.
Can you hear? Did you hear something?
Yes, sir.
No, sir.
Okay, because we are not able to directly share, let me try to play it once again with my mic.
I'm hearing.
Did you hear something?
Yes, yes, I'm hearing. Yes, sort of.
Yeah, sorry, because of the because I'm playing it from my speaker, coming into my mouse and coming to Zoom. I don't know. Yeah, so basically you can hear some pop music. I hope you heard some pop music. So the question is, how many sources can you hear? Can you tell me how many sources of sound were there? I'll play it once again. We'll try once again. Yeah, so can you hear? Oh, can you guess?
Yes,
Or
we hear some sounds.
yeah, some sound. Yeah, but so basically, if you try to identify how many sounds were there, there was a vocalist who was singing. There were some instruments. There were drums. There was a guitar. There was a bass guitar. There were some drums and some other instruments. Okay, go to next slide, please. So many of us listen to music, right? All of us enjoy music. I think most people enjoy music, but modern music production is a very complicated process. It can be as technical as you want, and it can be as amateur as you want. It goes from all the whole spectrum is there. So if you see on the screen, oops. So if you see on the screen, the top figure here, okay, you cannot see my mouse. The top figure where 3 guitarists are playing, they are playing inside a recording studio, inside a soundproof booth. And there are microphones which collect, so there are at least 3 mics which you can see. And mostly they're probably singing also. And their guitars are connected to pickup, to a pick, so that there are the guitar tracks also get recorded. On the top left, from the top right, you can see a sound engineer sitting in a mixing console, and inside the sound booth you can see 2 people singing. And so the sound engineer is basically using the mixing console. He is able to control the mix. That is, he's able to control adjust the frequency response and the gain of each input, each channel. So here in this case, there are 2 singers, so there must be at least 2 channels, and each mic of each singer is connected to 1 channel. And so the sound engineer is adjusting the mix so that both the sounds are clearly heard. Okay. It's more relevant. I mean, may not be in this picture, but like for example, if there are drums and if there is a bass guitar and a drum, a lot of their frequencies will overlap. So a sound engineer has to make sure by using an equalizer he will make sure that both the instruments are clearly visible. One is not masked by the other. By controlling the gain and by controlling the frequencies at what gain is there in each frequency, each channel can be controlled so that the output is more pleasing. It is so it is not just not just about how he mixes. There is also a aesthetic component also. The sound engineer, along with the music producer or the music director, they will give also some aesthetics. And modern studios, I mean, like in the current age, recording need not always happen physically in the same recording studio. So, for example, if a band wants to record a song, the different band members could be in different places, okay, and they all will contribute one particular channel or one particular track. And next slide, please. And suppose there are 4-5 tracks, 4-5 tracks are there. Maybe a couple of vocalists, maybe a guitarist, maybe drums. So all those tracks will come to one place, and then so that tracks can be shared over the internet, and then it comes to the mixing engineer. So the sound engineer or the sound producer will use these separate tracks and use a software called DAW, a digital audio workstation. And using a DAW, the sound engineer mixes the sound. So that is how a final song is produced. Separate tracks from various instruments collected in one place or from various places are brought to the software like a DAW, and then the sound engineer will mix these mix and master. Mixing and mastering happens in software like DAW. Okay, so a lot of additional effects can be added to the DAW. Can give you a lot of other effects. You can add an echo effect. You can add some reverberation. You can spatially position the different sources so that they sound as if they're coming from different parts of the room. So a lot of things can be done. So that is how a commercial, like a professional music is produced in that way. Okay, next slide, please. Right. So now we saw how music is produced, right? Different tracks are mixed by a DAW, usually a DAW. And DAW can, like I said, you can do linear mixing, and you can also do a lot of non-linear mixing. A lot of non-linear effects also can happen. So finally, that is the music, which you can see on the left-hand side. So the music source separation is essentially doing the inverse process. Given the music, you want to isolate or you want to separate out the various sources. Now we are doing the inverse of what we just saw. Is the idea clear? What is music source separation? You want to separate out the sources, right? Right. Next slide, please. I'm not able to play it out. There are sound samples which I could have played, but right now I'm not able to play. Anyway, so where do you want to use music source separation? Lots of applications. I'm only touching some of them here. One of them is to restore old recordings. If you have old recordings on vinyl or tape or something which you want to, some of it may be damaged. So if you can make it digital and kind of separate out the sources, maybe then you can individually enhance each track, and then you can remix the recording and you can get the new version of the old recording. Music which is produced 50-60 years back, if it is damaged in some way, by trying to do source separation, you can make a new remix. Other tasks are music information retrieval. You have a large database of music, and you want to do some analysis of what kind of instruments are present, what kind of singers are present. So those kind of music information retrieval tasks can also be done using source separation. So source separation can be used as a pre-processing step. Okay, I'll not get into all applications, but a lot of applications are there. And a lot of media companies, for example, production companies, studios, TV channels, all of them have their own music production team, which uses various source separation. Okay, so now next slide, please. Yeah, so you all, I think, attended the sessions in the last few days in this workshop, and you must have all learned about spectrograms, right? So what is a spectrogram? A spectrogram is a time frequency representation of an input signal. So a quick recap, that first plot there shows a sinusoid, a sine wave, and its spectrogram is shown on the first row. The second column of the first row is giving you the spectrogram of a sinusoid. It has only a single frequency component, so that is why there is only one solid bar, right? In the spectrogram, the x-axis represents time and y-axis represents frequency. So in this sinusoid, there is only a single frequency which is there throughout time. So it gives you the time frequency plot. The second plot, the second row, gives you a square wave. And if you know a little bit about Fourier series, you can see that the square wave is a periodic signal, and it will have a Fourier series, and it will have a discrete spectra, which is essentially which has shape of a sink. And so that is what is seen in the second row, second column, which is the spectrogram of a sink. So you can see that there is a fundamental frequency, and there are multiple harmonics which exist throughout the time. The last plot, the last row, gives you a linear chirp signal. So a linear chirp is a signal where the frequency changes with time linearly, increases linearly with time. So now if you see the spectrogram, the last picture, the last subplot, it shows how the frequency increases with time in a linear fashion. So this is how you can read a spectrogram and what it tells you. Okay, what information you can get from the spectrogram? It tells you what frequencies are present when. So the last signal, the chirp, it shows that low frequencies are present in the initial part of the signal. Then some medium frequencies which are higher are there in the next, that will be between 1.5 to 2.5 seconds, the next 1 second. And the last 2.5 to 3.5 seconds, you've got frequencies in the range of like 18, 19 hertz. So you can see that how frequencies change with time. So that is how a spectrogram can be used. Next slide, please. Okay, so this is a spectrogram of a music piece. Okay, it is taken from this reference. You can read the paper. So essentially, it is color coded with respect to the source. So there are 4 sources here. There are vocals, drums, bass, and guitar. Most pop music data consists of these four stems. They are also called stems: vocal, drums, bass, and guitar. They are also called tracks or stems. So you can see the individual spectrograms on the right side. You can see the vocals. You can see the drum spectrogram, which looks more like an impulse, because the drum is like an impulse. There is bass. Bass is like a bass guitar. So you can again see some mild amount of harmonics. And then there is the acoustic guitar or the electric guitar, which has a high level of harmonics, the blue spectrogram. And that is the individual tracks. And then when you combine them using a DAW and all that, and finally you see the spectrogram of the music, it's a complete mix of all these, because all these frequencies overlap in time as well as in frequency. So inputs, the given tasks for a music source separation, for a music separation system is given the left hand side input spectrogram, you need to get the right hand side output spectrogram. As you can imagine, it's a very difficult task. Okay, it is not trivial. It's a very challenging problem. And before we get into how we can solve such a problem, we should look at how humans do it. Next slide. So music source separation is in some sense, a special case of what is known as a blind source separation problem. And humans are pretty good at it. So it is a very famous problem in signal processing, neuroscience. A lot of neuroscientists and engineers have looked at what is known as a cocktail party problem. So in a party, right, when there are a lot of people talking, you can easily listen to one conversation. You can speak to the person in front of you, and whereas in the background there are so many other conversations happening, but you are able to concentrate on one particular person. We are able to easily have a sustained conversation in a party. And how are we able to do this? It is because, I mean, there are no exact answers. This is a very challenging problem which neuroscientists have tried to answer, but essentially it is done by the brain. Our brains are able to keep what is relevant and throw out what is the rest. Okay, so remember that whatever we hear and whatever we are able to say, it is done by our brain. The ear is giving us the data, but it is the brain which is processing it, and the brain which is able to separate out and keep what is relevant and keep what is not. Next slide, please. So let's mathematically formulate this problem in a very simple setting. So here now you can see n sources, and they are all linearly mixed in some simple fashion. We are taking a linear combination of all of these n sources, and we are getting an output signal, the x of t. X of t is what is observed, which is, it is a linear combination of these n sources. Okay, so now in source separation, we have to do the inverse. We are given x, from x, we have to get the S1, S2, Sn. Next slide, please. Next slide. Yeah. So now, here we are going to have one more assumption. We are having multiple observations, not just one observation. We are having not just one x, we are having multiple x's. So if you see the equation on the left hand side, the top equation shows you one such x of t, which is a linear combination of the various sources. Now suppose there are multiple such x of t's, x1, x2, up to xn. And here in this case, n, the small n, represents the number of sources, and also it represents the number of observations. So in that sense, basically what it means is there are 3 speakers in the room, and we have 3 microphones. 3 microphones are capturing, 3 speakers are speaking among themselves, and there are 3 microphones kept at a distance, and each mic is capturing the mixture from all the 3 speakers. So the x1, x2, x3 are the 3 mixtures which are observed, and s1, s2, s3 are the 3 speech which are spoken by the speakers. And now we are going to assume that the mixture is a linear combination of the sources, and we can represent this system as a linear equation, x is equal to as, which is shown on the right hand side. X is a vector, A is a matrix, and S is also a vector. So in this case, just to make things easy, we are assuming that the number of sources is equal to the number of observations. That is, number of mics is equal to the number of sources. So X equal to AS. A represents the mixing matrix. Okay, next slide, please. So now, given this signal model, given x equal to as, we want to now get an estimate of s, which is shown in the right hand side, s hat, and we're going to say s hat is equal to some w of x. And what is this w? W is your unmixing matrix, which is essentially something like a inverse of a, right? So if this equation is valid, it means that x equal to as, and if you want to get back the s, you have to find the inverse of a, which is w. Can you go to the next slide? Okay. Okay. Right. So our question is now to estimate the w, which is kind of inverse of a, because see, in general, given this a, please can you come back to the previous slide? Sorry. Previous slide, please. Yeah. In this case, what is known to us? We know only x. We don't know a. We don't know s. Okay. So it's an underdetermined system. We have more unknowns than observations. So in general, the inverse of A, there is no guarantee that the A inverse will exist. So we have to use some tricks, or we have to make some strong assumptions to get the inverse away. Okay. Next slide, please. So, okay. Okay, so blind source separation is a problem which a lot of people have looked at over the last 50 years. And there are no exact solutions, but many solutions have been proposed. We will look at some of them. I mean, okay, Dr. Dash, are you there? Yes.
Yes, sir.
How much time do I have? 1 hour or?
Yes, sir. 1:30 up to 1:30. No.
Up to 1:30. Okay.
Yeah.
So I might have to skip some of the things. Okay. Okay.
Yes,
Fine.
sir.
Yeah. Okay. So a lot of methods have been there for blind source separations, and since it's a difficult problem, many of them are approximate methods. So, for example, traditional methods, starting with independent component analysis, ICA. ICA came in the early 2000, late 1990s or 2005 or something. It came 2000, early 2000, where ICA became popular, and other
You are not audible, sir. Sir, you are not audible. I think mute. I think due to the net problem only in Linux that is not shared. Not, I think, any other things. Sir, you are not audible. Sir, you are not audible. Okay, okay, fine, fine. Yes, yes, that's the problem actually. Net problem and that Zoom problem. That some problem is there. Okay. Should I stop sharing? Or okay. Okay, okay, fine. Okay, sir is joining. Okay. So Zoom class is there in his system. He is joining.
Can you hear me now?
Yes, sir. Yes, sir.
Okay. Let me open my slides here. Okay, so we were talking about ICA, and there are other techniques, even principal component analysis, PCA can also be used. I mean, so I will not explain everything. I will just touch upon one or two techniques in the traditional methods. I'll skip ICA. I'll just very briefly mention what it is. I will touch a little bit on NMF, non-negative matrix factorization. Yeah, so let's go to the next slides. And okay, wait. And of course, many deep learning methods are there. Recent over the past 10 years, maybe most of source separation and blind source separation have been done by deep learning networks, and we will see some of that. Okay, yeah, next slide, please. So how do you evaluate a blind source separation system? There are some standard metrics which you can use. which is mostly we use what is known as the signal to distortion ratio, or SDR, which essentially tells you, if you see the equation on top, it gives the S hat of T is the estimated source. And that estimated source has got multiple components in it, including the target source and many other distortions. There could be interference, there could be noise, there could be artifacts. So these are all limitations of whatever algorithm you're using. None of the algorithms are perfect, and they will all of them will result in some artifacts, some additional events. So the SDR is kind of is a way to measure the outcome of a source separation system, and lower the SDR, it means it is poorer. So if you get higher SDR, it is good. Okay, next please. So let's very quickly look at ICA. So I will not get into details, but ICA essentially has, like I said, it was a popular method, came in the late 1990s and early 2000s. So here the ICA makes some strong assumptions that the number of sources should be equal to the number of observations. So that is N is equal to M. So that means the number of speakers should be equal to the number of microphones. So if you need to use ICA to separate 4 people talking, you need to have 4 mics. That is a major limitation. The second assumption which ICA makes is that sources are statistically independent. Okay, so that means speaker 1, 2, 3, 4 are independent. In some sense, for speech, maybe that assumption you can kind of say it is valid, but many times it is really not the case, because many times, even in speech, if there are 2 people talking, they don't talk at the same time, right? Usually one person talks, the other person listens, and so it's a dialogue, right? So overlapped speech is actually not very common. But in terms of music also, independence is really not really a strong assumption, is not really a good assumption with respect to music, because if you can imagine, if there are multiple sources, there is a vocalist, there are drums, there is a guitar, but they all will play in sync, right? So they cannot be independent. But still, even with these assumptions, ICA when it came, it was very popular, and it was a very nice technique, and it's very based on very sound theory. The main assumption which it makes is that none of the distributions have Gaussian. So they assume all these sources are random variables, and all of them are non-Gaussian, because the fundamental assumption of ICA is to increase the non-Gaussianity. So you can see next, you can read this reference. It's a very nice way to understand ICA, tutorial on ICA by somebody in Google. Next slide, please. So the procedure of ICA is you subtract the mean of each data, and you can do whitening of the data. Essentially, you make the covariance spherical, and then you have to find out the rotation matrix which optimizes independence. So it is posed as an optimization problem, and a solution is found by solving the optimization problem. Okay, essentially we are finding a matrix which, just like PCA finds a matrix which maximizes the variance, ICA finds a matrix which maximizes the independence of each source. So when you multiply a matrix by a vector, it is essentially a rotation operation. So finally, that is why we are trying to find the rotation matrix which optimizes this independence. Okay, next slide. I think so RPCA I will skip. I will not cover this because with lack of time. Let's come to the next topic on NMF. Yeah, non-negative matrix factorization, NMF. So this is also commonly used in music as well as speech source separation. Essentially, what happens in NMF is that you have a matrix X, and you are factorizing the matrix. X is equal to HW. The only constraint is that the matrices are non-negative. because that is why it is called non-negative matrix factorization. So for example, a spectrogram which is essentially the power spectrum of an audio signal is all non-negative values. So you can use this method to decompose a spectrogram. So so the very initial work on using NMF on source separation or in music transcription was this is the paper which I have given here, which is in which is by Paris Maragdis. So here basically what was done in this paper is that a given piano melody is decomposed into tones. So if you have, if you know how to, if some of you know how to read music, it basically tells you what tones have to be played at what time. So given the audio data in the form of a spectrogram, and if you decompose this into HW, H will form a set of basis vectors and W will form a set of activations. Let me see if I have a slide on activations. Yes, we will see that slide a bit later, but we'll come back to it. But essentially what will happen is, if you see the rows here in the right hand figure shows 4 rows, and the columns of W show the activations. So basically the first column, every note in the piano is a linear combination of the 4 rows, which is the rows of H, multiplied by the activations of each column of W. Okay, so it's a linear combination that we'll see in the next slide. Yeah, please come to the next slide. So the motivation of NMF is from use of parts-based representation. So essentially, again, this concept came from neuroscience. Essentially, what we see, how do we identify something? How does the brain? So this is a theory. We really don't know whether this is how the brain works. But one of the models of recognizing things, how can the brain recognize things? So the idea is that the brain recognizes things by using parts. It's a sum of parts. So for example, a person's face consists of, so if you want to recognize somebody's face, your brain is making associations with the eyes, nose, lips, hair, chin, etc. The different parts are what is so it's a combination of those parts which are enabling you to identify a particular person. So the fundamental parts are things like eyes, nose, chin, hair, etc. So by using various combinations of these parts, the brain is able to identify different people. Okay, so that is the whole idea of parts-based. Next slide, please. This I'll skip this. Next slide. So many algorithms are there for estimating these parts. For example, PCA is one, but PCA is basically decomposing it into 2 parts. There is a low rank subspace and there is a higher space. I mean, whatever is there in the low rank subspace, which contains most of the data, the remaining data is the residue. So it's got only 1 part. But PCA, the problem with PCA is that it is not really interpretable. Come to the next slide, please. Next slide. Next. 2 more slides you come. Next, skip this. Let's skip. Come to the next slide. Yeah, okay. Yeah. Let's stay at this slide. Let us go to the next slide. PCA. Yeah. Next slide. Yeah. So this slide is from the original NMF paper, which came, I think, in NMF paper came in 1999. Okay. So essentially, what we are doing here is we are decomposing this phase into a dictionary, which is represented by the big matrix on the left, and a set of activations. So essentially, this phase is made of a linear combination of all the columns of the big matrix. The dictionary matrix, you take a linear combination of all its columns, that linear combination is given by the activation matrix, which is there in the middle, and that matrix vector product is giving you this phase. So in this picture, they have shown it as a picture, actually as a picture, but actually if you see it from a data point of view, it is all of them are column vectors. So the phase on the right hand side can be viewed as a column vector. So you can take you can linearize this phase and make it as a column vector, and you can find out this column vector as a linear combination of the columns of the dictionary. So can you come back to 2 slides? One more back. Yeah, so this is what I wanted to emphasize. So this is an example. This slide maybe I should have shown it earlier, but essentially there is a dictionary D. It's come to the matrix at the bottom of the slide, which essentially shows D and A. D is a dictionary which is of size 3 cross 2, 3 rows, 2 columns. A is a vector which is of size 2 cross 1. And when you multiply this matrix with a vector dA, you are essentially taking a linear combination of the columns of D. Okay, so this is a standard way to understand a matrix vector product. A matrix vector product is nothing but a linear combination of the columns of D. So come next slide, please. Come back to the PCA slide. So that is next. Yeah. So essentially what we are saying is the dictionary is the big matrix here. The activations are the middle matrix. So a linear combination of all the columns of the dictionary with respect to the activations here is representing one particular image here. Okay, so this is the form of a PCA. But the main thing I want to bring your attention to is here in PCA. What can you make out? What can you make out? The basis vectors. The basis vectors are some you really cannot make out anything except for that first basis vector, which is essentially like the average, which is essentially the mean of the data. So this PCA matrix is created with some data, and that first column, the first row and column, the first entry in that matrix is essentially the mean of all the data. It is the mean phase. The remaining entries of the basis have no meaning. So come back to the previous slide, please. Whereas if you use NMF, for example, you can clearly see that NMF is trying to represent a phase as the dictionary elements of the phase are made out of parts. You can clearly see mouth parts. You can clearly see eyebrows. You can see eyes. In some cases, you can see the nose. In some cases, you can see the lips. So having a dictionary made out of non-negative matrix factorization we are able to interpret the dictionary in a better way. It is clearer. So we can give some physical meaning to the dictionary elements, which is not possible in other techniques like PCA because of the constraints we are putting on NMF. Because that non-negativity constraint means that combinations have to be a sum. There are no negative numbers. Whereas PCA, you can have positive and negative terms, both of them get cancelled each other. So you may not be able to physically interpret a meaning. Whereas that problem is not there in NMF. So because we can represent audio as spectrograms, NMF-based source separation of audios or NMF-based decomposition of audios was very common, at least for the past at least 10 years ago. After that, deep learning took over, but NMF gives you a very nice way of giving physical meaning to all of those dictionary items. Okay, go to the next slide, please. Next, I'll skip all this. PCA I've covered, VQ. Yeah. Okay, let's stop here. So we talked about some classical methods, which is ICA as well as NMF, which can be used to decompose a given signal into its different components. And source separation can be seen as one such problem. And hence NMF and ICA has been used extensively. Like I said, maybe 10-15 years ago, NMF and ICA were very commonly used techniques for source separation. So now we will look at particularly about music source separation. Next slide, please. So before we begin, let's talk about some of the existing models which are there. Now we are coming into the deep learning era. So this slide gives you in a snapshot some of the more recent results in music source separation and some of the commonly used models for source separation. So a lot of progress has happened in the last 5 years, let's say, with starting with the wave unit, which I will explain later during the talk. Wave unit and other models, for example, band split RNN and hybrid demux are state-of-the-art models which were released last year, which performs source separation. And most of the source separation has been done on Western music, on pop music, because of the availability of data. Okay, and like I mentioned about the evaluation metric, the SDR, source to distortion ratio. So you can see that as time goes, 2018 wave unit gave you an SDR of 3.2, whereas last year the band split RNN gave you a SDR of 9. Okay, so SDR essentially higher the better. So you can see SDR 9 is a pretty good number. So since I'm not directly on Zoom, I'm not able to play out the samples, but so you can see the quality of the models like band split RNN and hybrid demux are pretty good. So when you do source separation, the output which you get are pretty good. Okay, and most of this is driven by companies. Spotify, Google, Facebook, they are all doing active research in source separation, and many of these models, hybrid demux, for example, was released by Facebook. They have large companies with large computing resources are mostly driving this research. Yeah, next slide, please. So again, we'll come look at spectrogram. So what is so spectrogram gives you a very easy way to represent audio data. Okay, what are the good things? Good things about spectrogram, it is simple to implement. Essentially, that is the underlying data structure is just a matrix, a 2D array. But the problem with the spectrogram is that it completely loses phase information. So the spectrogram is done by taking Fourier transform and taking the magnitude of the Fourier transform. Fourier transform is complex, and essentially the spectrogram comprises of only the magnitude part. The phase of the complex number is completely ignored. So, so you can imagine when you do source separation, you are giving input. You want the output to be in time domain. You want the waveform, right? You want to play it out. You want to hear what the sources are. So essentially, you must be able to reconstruct from the spectrogram. You must be able to reconstruct the audio signal back, and that cannot be done without phase. So that is why using spectrogram gives you only half the information. Next slide. But since spectrogram is very easy to use and most people have used the spectrogram and phase is very difficult to process, what people do is they use a hack. Basically, you use a spectrogram and your source separation algorithm will estimate what is known as a mask. I've shown you a mask there, which is essentially a matrix which is of the same dimension as the spectrogram. If a spectrogram is of size m cross n, the mask will also be of size m cross n. Then you do a point-wise multiplication and you will get the source estimate. So essentially, by applying the mask on the spectrogram, we are removing out some of the other sources, and hopefully the mask is a good estimate of the spectrogram of one particular source. So like that, you have to estimate the masks of various sources, and you can use the separate spectrograms. And from where do you get the phase information? Because without the phase, you will not be able to reconstruct back the time domain signal. So for that, you use the phase from the mixture, the input X, right, which contains the source, the mixture of all the sources. You just take the phase of that
and then combine the mixture phase with the estimated spectrogram phase. The magnitude comes from this estimated spectrogram, the phase comes from the mixture, and then you take the inverse short time Fourier transform and you get back the audio signal in time domain. It's not perfect, but that it works reasonably well, and that is how people have used. Okay, next. So because of this inherent problem of using spectrograms, we wanted to, I mean, not we, the people who developed the wave unit model did not want to use Fourier transform at all. They wanted to directly use in the from the raw audio. So maybe in the previous talks you might have heard about models which directly work on the raw audio waveform. Okay, so in the benefit of this is that you do not have to explicitly model phase. Implicitly, it is taken care of by the model. You don't have to do a transform and get back into and get the phase. So that was how wave unit was proposed in 2018. Next slide, please. So this is the model of, this is how the wave unit looks like. You give mixture as input, the top left hand side, the yellow part. You give the mixture, successive modules decompose the audio by downsampling. You keep reducing the size of the audio by successive downsampling, and then finally you do a upsampling. It's a unit model. Some of you, if you know something about if you have used unit model is very commonly used in deep learning. So unit model looks like a U. It takes some input, it makes it small, and it reconstructs back the input. So by using this, so that same model is used here, but here the only difference is that rather than input spectrograms or images, we are inputting one-dimensional audio. So the convolution operations are 1D. And then, so the unit model, finally, the last layer, there is at the top of the green is essentially a difference output layer. At the end, enforces the mixture. So essentially, if there are k sources which you want to estimate, you estimate for k minus 1. And then the last source is given by m minus the sum of those k minus 1 sources, because m is the input mixture. M is the mixture, and the you estimate k minus 1 sources. You subtract the combination of the k minus 1 sources from the mixture to give you the last source. So this is how wave unit works. The code for wave unit is available. If you go to the author's website, you can download the code, and it is very simple to execute. Next, what type of data do we, now that I've told you a little bit about music source separation, and we've discussed one model, we discussed a couple of classical models, ICA, NMF, and then we also saw one deep learning model called NMF, called wave unit. So what kind of data sets are there for music source separation? So you can see on this slide, you can see a few commonly used data sets for music source separation. Most of these data sets are for Western music, mostly pop music. So it is very difficult actually to get data for music source separation, primarily because I will explain that later. We'll talk about that in a minute. But it is very expensive to collect data for music source separation. So whatever data sets we have, MuseDB is the second entry there. MuseDB 18 is one of the most commonly used data sets for music source separation, and it has got 4 instruments. And it's not very big. It has got 236 seconds only of data, but you can use it to build source separation models. So these are the commonly used data sets for music source separation. This was a demonstration of the hybrid demux model, which gives some particular output, but since I cannot play the audio, I will skip that. So let's go to the next slide. So this is a kind of summary of what we just spoke. We talked about music source separation. We talked about classical as well as deep learning methods. We looked at state-of-the-art, some of the state-of-the-art methods, and we looked at data sets. Okay. And like I said, most of these data sets are for pop music. So they are, so as with any deep learning model, right? When you have data sets on one particular type of data, they do not generalize well to other sets of data. Okay, so at this point, I will take a short pause, and if there are any questions, I can answer. If there are any questions, you can please ask.
Yes, any question from the participant? Shankar, anyone?
Uh, Good afternoon, sir. This is Randeep. Actually, I am working on music sets,
Okay.
especially on Indian music. Sir,
Yeah.
can you please guide me if how can I, especially in the mood and sentiments analysis, how can I get it done with the Indian music or Indian classical genre music? How it can be
I
done?
will touch upon Indian music in the next once this is over, but I don't have an answer to your question yet. But I will talk about
Okay.
Indian music in a minute. Yeah.
Okay,
Any
sir.
other questions? Any other questions from others? Okay, then let's continue. Next slide. So the problem was with the data set, right? Because most of the data sets were on pop music. So now coming to what Randeep was saying, India also has a lot of music traditions, right? We've got Hindustani, Carnatic music, so many music traditions are there, and each state has its own folk music. So many types of music culture is very rich in India. So we wanted to see how we can develop source separation systems for Indian music. So one, of course, we need data. And so in 2021, a data set was released called Saraga, which is a data set for Indian music. And it supports source separation research to some extent because it has got multi-track recordings. So you remember I told you that whenever you want to do source separation, you need to have multiple tracks because that is your output, right? So it has multiple tracks. But the problem with this data is, like I said, getting data is difficult. And so this data set was recorded from live concerts. Okay, that creates other problems that I will tell you what. Next slide. So let's concentrate on Carnatic music because that is the music which I'm more familiar with. It is so for those of you who do not know, Carnatic music is music which is there in the South India, and a typical Carnatic music concert looks like this. There is a vocalist, and there is usually a violinist and a percussion instrument. Usually it's the mridangam. So these three are the three main components of vocal Carnatic music. There is also a tanpura. These days, the tanpura is usually a electronic shruti box, which he is playing there. You can see that white thing. So that is the tanpura, which gives you the drone, which is the tonic, which gives you the background scale at which, with respect to which all the other musicians play. So I mentioned about Saraga data, right? The data set which we have for Indian classical music. Now, Saraga is collected from live recordings in concerts. It is not done in a studio. So in studio, you can see there is a lot of soundproofing and, you can isolate each track from other tracks. But in a live concert, that is not possible. So to build source separation data, to build source separation models, we need data. And to have data, we need good data. So the only data set we have currently is Saraga, and that Saraga suffers from bleeding. This is because now if you see the picture there, the mridangam artist is playing. There is a mic in front of the mridangam, but that mic picks up mridangam, but it also picks up the vocalist and it also picks up the violin. That is shown in the left hand on the figure on the right hand side. So the mic meant for mridangam picks up other sources also. They are not isolated. Whereas in a recording studio, if you put every instrument in a separate booth, or if they are separately recorded and mixed later, the problem of interference will not be there. The problem here in a dataset like Saraga is that there is interference. Okay, one source interferes with the other source. So it is this artifact is called bleeding. It is also called bleeding or interference. Next slide. So now, so I mentioned about my student Rajesh, who wanted to work in music source separation, but even before he started, we found out that there is no data set, and we found out about Saraga. But the problem with Saraga is that it has got bleeding, interference. So the focus of Rajesh's thesis was on to develop interference reduction. So given on the left hand side, you can see the various tracks: vocal track, bass, drums, others. This is of course for pop music. When you have vocals which are interfered with the other stems, bass, drums, others, you don't have clean vocals, you have vocal with interference. You want to pass it through this interference reduction system and get clean source estimates. Okay, so that is the problem which we are trying to address here. We are trying to get an audio which has got interference from other sources, and then we want to get the clean source back. You want to remove, so in other words, if the vocal track has got interference from bass, drums and others, we want to remove all the bass, drum and others and get back only the clean vocal. Next. And if you have this music interference reduction system, you can collect data from live concerts, and then you can clean them up using the interference reduction system, and they can be used as a input to the music source separation system. And then we can train the music source separation system. Essentially, the interference reduction can be used as a pre-processing to music source separation. So that is the idea here. Next. Okay, hello.
Yes, sir.
Yeah, I think my Zoom has again crashed. Can you hear me?
Yes, yeah.
Okay. I have to.
Rejoin again. Right?
Yeah, I'll have to rejoin again, but I'm not able to come out. Let me see. Hold on, please.
Yes. Just wait for a second. Sir is joining again. Again, Zoom has crashed.
Yeah, can you hear me?
Yes, sir.
Yeah, I'm sorry about this. Anyway, so you've shared the screen, no? Okay. Yeah, okay. So music source separation is, so I was telling about the interference reduction and how it can be used as a music source separation. So this slide kind of gives you the contrast between a music source separation system and a interference reduction system. So the music source separation system has got, you give the mixture as input, whereas in the interference reduction system, you give a single track with interference as input, and it gives you the cleaned up sources as cleaned up tracks as output. Okay, next slide, please. So one way of developing a interference reduction system is by looking at interference as noise. So we have a microphone, we have a source plus some noise. So here the N of T here represents the input from other sources. X of T is equal to S of T plus the actual source, and the noise represents the input from the other sources. Next slide. So we can use an autoencoder based architecture to remove the noise. So there are microphone recordings, so that this autoencoder is shown here. There is microphone input, microphone recordings as input with interference. You split the spectrogram into different columns. Hello?
Yes, sir.
Yes, sir.
Yeah. So split the spectrogram into different columns, and then give it as you can stack them here in this particular architecture. We had stacked them, and then you give it to an autoencoder with a bottleneck layer, and you have a decoder, again very similar to your unit, and you get back the so this autoencoder is trained with matching pairs. You have interference and you have input interference and output without interference. So like this, you train this autoencoder. And after you train the autoencoder, what it will do is, if given a noisy input, it will learn it by learning, it would have learned how to remove the noise. So give it a fresh input with noise, it will remove the noise and give you the cleaned up output. So that was the idea of this autoencoder. And next slide, please. So one more thing to do, but the problem with this kind of an autoencoder is that you need to make an autoencoder for every stem. So for input, for drums you need one, for vocal you need a different one. So a vocal autoencoder cannot be used to clean up interference in a violin stem. So since we did not want to have an isolated separate autoencoders for every stem, what we can do is we can try to make use of the other information. That is which is there in, we have multi-track recordings, right? We have recordings with multiple tracks, and one information is present in all the other tracks. So we have to try to use that information. So next slide, again coming back to the same mathematical model which we saw earlier. X is equal to lambda S, where X is my observed input. X are the sources which you need to estimate. Lambda is the mixing matrix. Interference matrix is the same as your mixing matrix. So now what we can do is we can estimate the matrix using a neural network. And once you have this matrix, you can take its pseudo inverse. Take a pseudo inverse, which is the least squared inverse of that matrix, and you can get the estimate of the sources. Next slide. So that is what we have done here with this neural network. There is this input, and then what the input learns, because this we are assuming a linear model here, the input interference is given, and then the mixing matrix is given as output. So the neural network learns an input with interference and learns and outputs a matrix which caused that interference. Essentially, we are learning the mixing matrix or the interference matrix. Interference matrix is estimated using the neural network. And then you can take the pseudo inverse to get you the estimate of the sources. So this kind of technique to find out an interference reduction can also be used, but the only drawback of this method is that the model we have is still linear. We are still using a linear model. Okay, next slide. But actual recordings, in concerts, for example, are typically very much non-linear. There are a lot of room reverberations and room responses which add up, which make our linear model which is the linear model which we have, is not really a very useful model, because most practical recordings in concerts, like the picture which you see on the right, so many times concerts are held in such locations where there is a lot of people, pillars are there are reflections from the walls. So all those sounds will interfere with the recording. So we are never going to have a linear response. So that is the limitation of the model which I just showed. Okay, so we can somehow overcome that by simulating room reverberations. So there are packages available, Python packages are available by which you can estimate reverberations in a room, and you can simulate those reverberations, and you can add those reverberations to the recordings, so that you can get recordings with interference and room reverberation. And by using that data, you can train the neural network, and hopefully that will work in a random recording like this. Okay. So next slide. So Rajesh, in his thesis work, he had done some such results. He had done some experiments on this, and we have compared this with some other existing work. There is a algorithm called CAMIR, which is used for interference reduction, and we have compared whatever neural network based method which we have with this method, and you can see that the neural network based method, which is called TUNet, the purple, gives you significantly higher SDRs as compared to methods like CAMIR. And the various x-axis, the various plots on the x-axis gives you the data sets which we have used, MuseDB, and MuseDB-R is the reverberated version of MuseDB-R. Is reverberation, it is MuseDB with room reverberations. So we have used a Python package to create reverberations in the room, and added it artificially to MuseDB and created MuseDB with reverberation. And then the algorithm was done to perform interference reduction on the reverberated data. Next slide. This is actually my last slide. So you can see how the reverberation and the interference is removed. The highlighted part of the spectrogram gives you the output which is present in the input. And if you see the bottom spectrogram, you can see that that component is completely removed, because this is a vocal source, and that interference which you can see at the bottom is from some other source, some harmonic source, some violin or something, and that has been completely removed by using this method. Okay, so I mean, time is almost up, so I will stop here at this point. And in this talk, we have mostly covered source separation, and we were talking about techniques to develop data for source separation. We looked at existing data sets for pop music, but if you want to use source separation on other types of data, we need the data, and one way of getting the data is by recording from live concerts. The problem with live concerts is that it has got interference. And by using interference reduction techniques, which I discussed, it is possible to somehow reduce the interference and use that data to build source separation models. Okay. Yeah, at this point I will stop, and if there are any questions, I will take. That the student who asked me a question about Indian music. So you were asking something about, yeah.
Sir, yes, sir.
Yes.
I just want to interfere. Sorry for that.
Yeah, please.
I just want to ask how it can be very different about recording from a pop music and a recording from an Indian music. To classify these two genres, how this can be very different, because both of them, if the live music is taken into account, everything is recorded in one channel, and all the instruments, like you said, the mridangam, the vocalist, the violinist, the ghatam, whatever in the South Carnatic music is there in the classical music, it is recorded in one channel. Especially in the pop live music also, there are various instruments played like drum, guitars, piano, organs, and the vocalist are also there. Both are of the same, means the recording channels are same.
No. All of them are separate. Even in the Carnatic music, Every instrument will have its own mic.
Yes, sir. That's what I'm saying. Every
Yeah.
instrument has its own mic, but the mixer comes as one in the live
Mixture
music.
sounds as one. Yeah, mixture sounds as one.
Yes.
But what is your question? What is the question?
I'm asking if the model which is classifying or disintegrating the live music of the pop musics,
Huh?
the live outputs of the pop music,
Huh?
that can be used in this Indian form of live music to identify or the disintegrate the live music coming from different channels.
That is the problem with any deep learning method, right? It depends on the data. If the distribution of the data is different, if you train a model for classification of images, some AlexNet or some VGG network or ResNet or some modern network for classification of images, can you use that same network to classify X-rays?
No.
The same problem here because of the domain shift.
No,
So
sir. My exact question is, for example, in a pop music, there are three instruments used like guitar, one is
okay.
drums, and there is a vocalist. Okay. And the output coming as one.
Yes.
And exactly in the South Indian Carnatic music, there is a
Yes.
mridangam, there is a violin, and there is a vocalist.
Yes.
And the output coming as one.
Yes.
So the methodologies used to extract disintegrate the live pop music that can be used here in Indian music output.
The methodology used for
The disintegrating.
No. Are you
the
talking? No. Let me clarify here. Are you talking about source separation or are you talking about interference reduction? They are two
interference
different things.
reduction. Yes, sir. Source reduction. First, I'm talking about the source reduction, source separation.
Okay, source separation. So the input to any source separation is a mixture and output other various tracks.
Yes, sir.
What is your question? You are asking the source separation used for pop music. Why it cannot
be used in the Indian music?
That is the problem I told you about the domain shift. Pop music is very different. The genre of pop music is completely different from classical music.
So that genre might be different, but the output that is coming, that is the same.
No, you are telling about you are telling about only the input and the output. That is the same here. Input here is a mixture. Input there also is a mixture.
Sir. Yes, sir.
But that is not the objective here, right? Yes, but that neural network will not perform well. You will get some orbit output. For example, in pop music, for example, there is no violin. So what will you use in classical music now? If you have a modern pop music based system like hybrid demux, which works very well for pop music, it will give you output. It will give you an output for guitar. Now, what is the corresponding? What is corresponding to guitar in classical music?
Mohan Veena.
Sorry? No.
Mohan Veena.
No. That depends on what type of data you have, right? If you are looking at so you are trying to create a problem which is suiting your model. That is not what we want. Typically, most of the time we have some existing recordings which is already recorded, and we have some model which is already trained on some data. How will you use? How you in general you will not be able to use that model on this data.
Okay.
That is what I'm saying.
So for now, apart from Saraga, there is no other way to for the recording or disintegrating Indian music. That's what you're saying. Yeah,
see, there was a very big project by this Professor Xavier Zera, who was there in the who was one of the co-authors of the Saraga paper. You can refer to that paper. But there is a project called Music Brains. Music Brains. Their website is available. You can also go to Professor Xavier Zera's website. He has done he's a Spanish professor, but he has done a lot of work on Indian music. So you can go to his website, and there are links to 1 or 2 projects where some data is available for Indian music. So based on what is the problem you're trying to solve, you can go there and see if the data there is suitable for you or not. But other than this data which is there with Professor Zera and this Saraga data set which I talked about, there is no other standard data set for Indian music.
Okay, sir. Okay, got it.
Yeah.
Any question from others? Dipshankar?
Yes, sir. I have a question.
Yes,
Sir, sir, in that interference reduction, you have first used that bottleneck structure. In bottleneck structure, we are doing what? We are doing, preparing for every type of instrument, and we are extracting that output, right? In
Yes, we are
bottleneck.
creating an autoencoder for every stem. So if there is a vocal stem with interference, we create an autoencoder for that. If there is a drum stem with interference, we create a separate autoencoder for that. So for if you have 5 stems, you need 5 separate autoencoders.
Okay, but these different tracks are created by how? Firstly, we are passing it by separation model, then we are getting that mixed interference output for it. Is then we are parsing.
No. Interference comes only in the context of live recording. So if you are recording the data from a live concert, not in a studio.
Yes, sir. Hello,
if
sir.
you are recording it in a concert and not in a studio, interference will come. Whereas if you're doing it in a studio, the sources are isolated. If you're collecting the data and mixing it separately, isolated sources will not have interference. So what was your question?
So my question is that, so when we are doing that interference separation via bottleneck method, we first have to identify which instruments are used. Then we have to first train it by using interference pitch of that different instruments. Then we have to prepare the result and put it in the mixed sample to remove the interference.
Yes.
Okay. Oh, and that is solved by that new method where
that is partially solved, not fully solved, because it is the mixing is still considered as linear because we are taking a pseudo inverse of that matrix. No, that the signal model is still a linear model. So it works to some extent, but it has its limitations. Yeah, but
So one more thing.
if you use the second method, you do not need to create separate autoencoders. You can create just one model which will accept all the stems as input, and it will give you separate outputs.
Okay.
Yes.
So one more thing, if I can get the data from the studio recordings, which every instrument is being recorded with different channels, then in that case, I can get my results.
Yes, if you can get that data, then that is the best case. That is how MuseDB was created. MuseDB was created by isolatedly recording all the devices, all the instruments, all the sources in a studio. And that is why that dataset is so popular. The problem in collecting data is because artists are very busy. Artists is very difficult to get the data from artists, and there is copyright and many other issues. No? So very few artists are willing to just like that share data. So
sir, why am I asking this? Because I myself is an artist. I'm a singer professionally also.
Okay.
So I have a lot of data sets like recorded in studios, which have different channels of all these like vocals and instruments are all the different. So if I could assemble those data, or I can get those data from whatever sources I also have from the other artists too. My aim for what I'm targeting for source separation, I already got a separated source right from that.
Yeah. Okay.
Then noise reduction and getting. My point is to how to identify the moods and the analysis. Sentiment analysis. How can I do it from there?
Okay, actually, we should talk more about it if you are interested. And
Yes,
I think we will.
Okay, sir.
Yeah. So
yeah,
I think
okay, sir.
Yeah. So we should definitely follow up, and we should try to see what we can do, and
sure,
we can talk a little more in depth. Yeah, please.
Sure, sir. Okay.
Are you a student or are you a faculty member?
Sir, I'm working.
Just now I told he has joined as a PhD research scholar under me.
Okay.
And he's also working as an employee in this KIT University for last 15 years.
Okay.
Just enrolled as a research scholar.
Okay. Very nice to hear. Okay. Yeah, but we should definitely talk more about it.
Yes. I just told you.
Sure, sir.
Yes.
I think no more questions. We should stop here, sir.
Thank you. And
thank you very much.
I apologize for the
No, sir, it's happened.
because Linux is not. I think Zoom is not supported fully on Linux.
Linux, yeah, something is there. Anyway, the session was very informative, and I think any students want to do some work on music, definitely they will contact me and I will definitely contact you.
Yeah, and you can please share the slides. I've already shared the slides with you.
Yes,
You
yes,
can
I will share it.
share it with the students if anybody is interested.
Thank you. Thank you.
References. Okay.
Namaskar.
Thank you so much. Thank you, everybody.
Thank you, sir.
So.
So today there is no more sessions. I think this is the last session today. Only 2 sessions are there today. Am I right, Deep Sangan?
Yes, sir. Yes, sir. Today no session is there.
With the attendance, and tomorrow again will be fine. So I'll let me share the slide with you now, because I have only one slide of this person. I'm going to share it in the group. Okay. Thank you very much. And recording, definitely we are going to upload all the recordings in the YouTube, and you are supposed to give you the links of the YouTube. Okay. So don't worry for the study material. All the YouTube, this sessions are recorded, and I'm going to share it in the YouTube, and the link will be shared with you. Okay. You can watch it. Thank you very much.
Thank you, sir.